the exact millisecond you tap your screen to open a high-end mobile game, your phone initiates a massive, invisible chain of calculations. To render the digital world you see, the device has to calculate lighting physics, map textural details onto surrounding buildings, and generate spatial shadows for your character. It does all of this from scratch, and it updates that math 60 times every single second. The smooth, seamless experience playing out on the glass is a highly effective illusion. It masks a specialized division of hardware labor operating just underneath the surface. The center of that operation is the Central Processing Unit, or CPU. It acts as the general manager of your phone, running the operating system, handling your keystrokes, and managing background tasks. The CPU is built for pure, rapid calculation. When you see a processor advertised with a clock speed of 3.3 gigahertz, the giga means billion. That specific CPU executes 3.3 billion individual cycles every single second. This visualization shows what one of those cycles actually looks like. At a physical level, the CPU consists of microscopic transistors acting as switches. The line spikes to a high voltage peak, representing a binary 1, and drops back down to a low voltage baseline, representing a 0. That single high to low switch constitutes one cycle, executing one microscopic instruction. But here is the catch. Despite processing billions of those commands a second, forcing a CPU to render a game's graphics entirely by itself results in a frozen, unplayable slideshow. When it comes to rendering complex visuals, raw calculation speed is the wrong tool for the job. The issue comes down to the physical design of the CPU. It is built as a sequential processor, taking complex instructions and solving them one by one in a strict step-by-step order. This flowchart demonstrates why that creates a bottleneck in gaming. To load an environment, the CPU has to work in a single file line. First, it loads the building. Only when that finishes can it load the character, and then finally, the shadow. In a video game, that delay creates massive lag. Engineers optimized this workflow by developing what is known as the big little architecture. Instead of making all the cores identical, they divided the labor. A few high-power big cores take on heavy logic tasks like video editing and core gameplay. Meanwhile, efficient little cores manage lighter tasks like background messaging apps to keep the primary line moving quickly. The CPU manages linear problem-solving with extreme efficiency. However, that physical design hits a wall the moment a task requires spatial scale rather than sequential logic. Imagine hiring a master-level painter to paint a massive wall. They will execute the job flawlessly, carefully patching holes and applying perfect coats of paint. But they have to do it one painstakingly precise brushstroke at a time. To solve this, your phone relies on a second piece of hardware, the Graphics Processing Unit, or GPU. It is engineered specifically to break the CPU's sequential bottleneck. This structural comparison shows the difference. On the left are the heavy, complex nodes of the CPU. The GPU, on the right, trades away those complex logic capabilities for thousands of simplified, smaller processing cores. Rather than using one master painter, the GPU deploys an army of thousands of workers. Each one is assigned to paint exactly 1 square inch of the wall at the exact same moment. On your smartphone, those square inches are pixels. A high-end game puts millions of pixels on the screen at once, and every single one needs a specific color and texture. The GPU assigns a tiny core to calculate the shifting visuals for each pixel simultaneously. The GPU achieves smooth graphics by trading complex intelligence for brute force synchronized spatial volume. The CPU and GPU exist together on a single microscopic piece of silicon called a system on chip, or SoC. That same shared space also houses specialized neural processing units, or TPUs, on Google devices. Their sole job is executing on-device AI tasks, like live translation and night mode photography, processing the math locally instead of bouncing it to a cloud server. Because this tiny piece of silicon handles so much, companies aggressively market their overall power using nanometer metrics, advertising 4 nanometer or 3 nanometer chips as a sign of superiority. Historically, that nanometer rating measured the physical distance between transistors. Today, the label is a generational marketing term used to denote the overall efficiency improvements of the entire system on chip. Evaluating a phone's capabilities based on a single marketing number ignores the deeply integrated hardware ecosystem required to run modern software. When you load into a demanding mobile game, you push that ecosystem to its limit, triggering a real-time division of labor. Backstage, the CPU acts as the logic engine. It rapidly calculates player hitboxes, manages the physics engine, and updates the mathematical rules of the digital world. Simultaneously, the GPU takes that linear math and acts as the visualizer, painting the millions of pixels required to make that world visible to the human eye. The rapid single-file management of the CPU perfectly interlocks with the massive synchronized swarm logic of the GPU. Your smartphone operates through a system of delegated labor, precisely coordinated across billions of transistors every 60th of a second.